As I said, I'm Philipp Müller and I'm a PhD student at the Institute for Baustoff at ETH Zurich, where I'm supervised by Falk, Wittel and David Kammer. And for cracking is a multi-scale phenomenon that starts at the smallest scales, where the microcracks behave more or less independent, and then coalesce into each other, and then finally localize, and then forming big macroscopic crack. And then, however, the microstructure has a big influence in this whole process, because in the beginning the crack grows, and then the aggregates in concrete acts as obstacle, which basically can deflect the crack or even halt the crack. But sometimes the crack is able to go through aggregate. However, also in the post-failure behavior, I mean, also after the crack has gone through a region, the microstructure still plays an important role, because you see, you never have seen a clean surface crack. Also, a clean surface of a crack in concrete. It's always rough, basically. And this can interlock with each other and then provide some form of strength. And in my thesis, I'm developing a new method which is basically able to capture this whole process and tie it through the entire life of the crack to the same microstructure. And it initially begins in the continuum, where in the uncracked domain, the material is resolved as a continuum, and the microcracks in it are modeled by a continuum damage model. However, once a critical level of damage has been reached, then the continuum model, together with its damage, are transformed to a discrete one, where then the entire cracking and the microstructure is handled. And this is also the topic of my presentation, and this mapping I call forward transformation, and there is also backward transformation. However, we will now go to the forward transformation, and the forward transformation is essentially, you have a continuum representation of a domain, and you want to with damage, and you want to transform it into a discrete representation that has a damage which is in some way similar to the continuum, to the damage that was present inside the continuum one. And first of all, why is this consistency, this damage preserving important? Although the damage has not yet localized, it still has degraded the material performance. I mean, it's essentially becomes weaker. So we have to consider it to be consistent. However, before we can do that, there are several challenges that we have to overcome. First, as I have mentioned, the discrete damage must match in some way the continuum damage. However, this operation is not unique, since the continuum is essentially a low information content representation, and the discrete representation, where you basically have everything, is a high information content. So you basically have to create information, and this is not possible, so you have to basically be happy with something that matches in a statistical way. I mean, when you produce 10,000 transformations, then it will be correct, the mean of at least the mean. So for representing the continuum, we are using standard finite element together with a damage model, which basically introduces this D here, and this here is the unit tensor. So one minus, in the continuum you would have basically one minus, in the 1D case you would have basically here 1 minus D, where D equals 0 means no damage, and D equals 1 means absolute damage, you have lost every stiffness. In addition, you also need to provide some evolution law of this damage tensor, which depends on kappa, which is the history or state variable inside the continuum. For representing the discrete representation at the moment, I'm using a regular triangular framework made of Bernoulli beams. And while in the continuum, the damage is represented by the growing of d, I mean basically d goes from 0 to 1. In the discrete one, damage is represented by the basically successive removal of beams. And a beam is removed when its failure criteria is fulfilled. And you see here it combines the elongation and the bending that the beam experiences. And the damage, the failure criteria is parameterized by these two values, epsilon ITH and phi ITH, which is the elongation and bending threshold respectively. And these values are unique for each beam, so each beam has its own, and they are drawn from a Wittel distribution. So, for doing our task, we basically need two things. First of all, we need an evolution law for d that is applicable inside the continuum. And this law basically tells us, you see, in the beginning, we just have the continuum. We don't have the discrete representation. However, this d then tells us how the continuum representation will fail, or would fail if it would be there. And here we also define that kappa is the maximal principal strain the specimen has seen thus far. And then the second thing is we need a link between the continuum and discrete representation. And here we have R, which we say is the state variable in the discrete representation. You see, kappa and R represent basically the same damage, however different viewpoints. One's a continuum and one's a discrete viewpoint. And R, we define it as the fraction of failed beams, and we say that our link depends on kappa and d. So, and how we will find this, these two representations are, these two functions R and d. So here would actually be a video where you would see that blue beams are popping up, which are basically the failed beams. So as I have mentioned, I'm a computer guy, so I don't have any tests. I did it on the computer. I basically created lots of these specimens, a bit bigger, and then I basically subjected them to various tests. Also, I mean, I basically have pulled them apart until they fail. And then I have used this very nice paper by Oliver Leblanc that allowed me to extract d from these measurements. And then based on that data, then I was able to fit d representations for d and r. So, for the material, I assume a brittle and disordered material, which is basically a consequence of using a large Wittel module, and I am restricting myself to 2D specimens. The strains are the tests are all performed displacement controlled with uniaxial strain tests. So I fix top and bottom, and then I pull at left and right. I also have done it to impose this strain into different directions, and then I basically use this formula to transform the strain. And I have used the finite element library Continuum for implementing this. This is a C++ framework, and to shortly describe the algorithm, each loading step, I use a static loading. So in a loading step, I first impose the final displacement on the boundary of the specimen. Then I compute the equilibrium position of all inner nodes, and then I evaluate the failure criteria. When there is one beam, at least one beam that fails, I remove the beam that has the largest failure value, and I repeat these cycles until no beam fails. And this is basically what I have done. So, and now after I have done that, I have skipped that, our target is to basically create damaged lattices from the beginning. So, how we do that? As I have mentioned, we start in the continuum. So we have a damage and a state variable. And then we can use our link, our R basically, to compute, to transform this continuum state variable to a discrete state variable. And since R is the number of the ratio of failed beams, we know how many beams we have to fail. However, the question remains which beam we should select. And now comes the statistics into play. We select them randomly. However, we do not select them arbitrarily, but we say that the probability that the beam is selected is inverse to its elongation threshold. This is basically the very logical conclusion that a weak beam should fail early. So, however, as it will turn out, this is not enough, and we need a second component, and this here is described by this scalar product, which basically takes into account the direction in which we pull. You see, Bi is the direction of the beam, also the unit direction of the beam, and T is the direction in which we pull. You can see this here. Here, this shows basically some failure state where we have pulled along the x direction. And you see that the majority of beams that have failed are horizontal. And this is basically what this scalar product does. It basically filters out beams that are not aligned with the direction in which we pull. So, and now we came to the results. Here, you see, we are in 2D. So the damage variable is actually a 2x2 matrix. And nobody can really plot or good plot 2x2 matrix, and so we plot the eigenvalues of the damaged tensor. And you see here, these are basically the naturally damaged specimen, basically where we really have pulled. And the blue line is the eigenvalue that is associated to the x direction, and the y, and the orange line is the one that is associated to the y direction, and as one can somehow expect that y is much less affected. And here you see a wireline plot. This basically tells you which beams have failed. You see, we have 3 different kinds of beam: horizontal and 2 inclined beams. And here you see that the majority, when we pull along the x direction, excuse me, I forgot to mention this. This here shows the state at the particular at the strain of 0.002. And you see that the majority of beams that have failed are horizontal beam, which is basically what I have told you, and that basically not, or just a very tiny fraction of the inclined beam have failed. And now we go to k equals 1. This is basically everything is weighted. Oh, excuse me, I forgot this. Here. You have this exponent k. This is so I call it damage weight, and it is basically to make this factor more important, to give it more weight. And here is k equals 1, and here you see that the damage in x direction is too low, while the damage in y direction is far too high. And here you see the reason. We see that we have damage that while the number of beams that have been selected is correct, we selected the wrong beams. You see, we have not selected enough horizontal beam, but we have selected way too much inclined beams. And so when we increase k, also meaning making the directional component more important, then you see that it gets better. Until at around 6 we get satisfactory results. My conclusion is that we are now able to generate in a consistent way damaged microstructure. However, you see, I only have studied uniaxial strain tests. I'm currently in the process of extending this to, let's say, multi-axial loading that occurs at the same time, also basically compositing damage modes. Yeah, it's somehow going, but yeah, beside that there is still a lot of work to do. You see, my method that I want to implement is basically, you see, I want to only transform a small part of the domain where damage has reached a critical part into a discrete domain. So I must use something for coupling, and currently want to use the Albeck method. And then I want to use the discrete domain, the discrete representation to capture this interlocking. And you cannot do that with beam. Beams are very good for some form of compression loading, but more appropriate for tensile loading. You see, you need classical dam, which has basically small spheres that are interacting together, and with that you can basically create a surface. However, as there is a forward transformation, there is also a backwards transformation, and you see, when the crack is over, then you have a big chunks of particles, which costs you a lot of computational power until you want to get rid of them. So you want to go back into a continuum representation, and for that you essentially homogenize it. So you must basically restore the continuum damage, and you need to use XFEM for capturing the crack. However, see, I want also to tie this behavior in this phase to the microstructure. So I basically retain the surface of basically the surface particles, and by that I get a super sophisticated traction separation law, which tells me how the crack surfaces interact with each other, and so I can basically also simulate the interlocking even after I have homogenized. So, excuse me. Thank you for your attention, and if you have any question, you can now ask them. I know the audience is maybe not perfect, but
okay. Thank you for your presentation. Any questions? You have one? Yeah.
Make a comment. You have used the final fundamental, right?
Mm-hmm.
But most probably, this is just a suggestion to use meshless methods. I don't know if you work with this or not. But
Yeah, I have worked with them.
all of these problems or issues really solved. I have already studied something like this about meshless methods.
Yeah.
And also about the final fundamental X and everything.
Yeah.
Who are boundary elements, all of this. At the end of the day, I understood that this kind of problem can be simulated by meshless method through local damage.
Mm-hmm.
And you can consider rate dependency and rate independency.
Yeah.
So you most probably you will not be in problem with your obstacle. It's just a comment.
Yeah.
Because meshless method is not using mesh.
I know that I used them in my master, but you don't really get basically, if I remember correctly, meshless method, they don't have, they just have sparse sampling of points that are floating around.
It is you need to, it's basically the final Kammer method, but you need to build your model, you need to remove the element and keep the Gauss points and the nodes. Yeah,
but you see, here in the DAG representation,
Mm-hmm.
I have a lot of particles. You see, an aggregate is then not represented by one big sphere, but by many spheres that are bound together, and so you can also handle aggregate fracture.
I think that's why I told you can use local damage model. You need to write a routine for that. But
Yes.
it's with MATLAB. Maybe if you are following FEM, if you are in the middle of the way, you can.
Yeah.
But it was just my experience.
Yeah.
Okay.
Thank you for the nice idea. I was wondering, so you're removing these connections, kind of distributed throughout this area, right?
So you're speaking about the discrete as a
Sorry, yes. Yeah, where you transform to the discrete representation.
Yes.
Yeah. But if you, in the end, want to model a crack,
Yeah.
should you make sure that the elements you're moving are somehow connected to each other?
Okay, I think I have forgotten to mention that. You see, basically, I want to transform before localization.
Okay.
You see, basically, I just went, so the damage is still diffusive. Then it's a bit easier.
I have also a question. Have you thought about assigning random cross-sectional area
No, they all have the same cross section, and they all also have the same elastic modulus, and I cannot remember what the E is.
Elastic.
No, the bending moment.
Area
The inertia of area. That's it. Yeah, they all have this is all the same.
I have one question.
Mm-hmm.
I think in the beginning you said that the application is for concrete material, and you referred the bending for the flexural in the first slide. I think. Yeah. Okay.
Yeah.
On this, but when you perform your I think simulation, you tested interaction.
Yes.
Tensor.
Mm-hmm.
Okay. But you are considering on bending because this is the most critical mode for concrete.
Yeah. Also, you see, basically, it's more like a material model, like anything else. But
yeah. But
bending,
when you put bending, you will have tensile and also compression.
Yeah, but in concrete, compression is usually not the problem, if I remember correctly.
Yeah, the tensile will be the critical part. Yeah. And another thing, you make this work only on 2D structures.
Yes.
You are considering moving for 3D?
Yeah, we were initially considering but then we realized it could be too much. But you see, 3D is definitely the long-term goal.
Okay. And another question. Today we are applying some cellular structures that we are sometimes producing with additive manufacturing. With this truss and this, do you think this will be a good model for these structures, cellular structures?
Yeah, technically yes. However, then you basically have to tune the transformation. Most likely you will have to tune the transformation, because then you cannot assume that then there is, you see, when the two layers met, then there could be a higher increase of damage than inside the material. So you must likely tune the transformation to better account for that.
Yeah, because one of the reference was one book of cellular structures that you showed.
Yeah, this is because this, here. Ashby and Gibson. This is because this is why I have basically the regular framework. Because the really next step will be to go to irregular frameworks.
Okay. We don't have more questions. We switch to the last presentation. It will be a video. And thanks again.